Hello everyone, it's September 29th. Alright, time to take a look at this 132 pattern. Given an array of n integers, nums, a 132 pattern is a subsequence of 3 integers, this, and this, such that I smaller than j smaller than k, and numbers I smaller than k smaller than j. Oh, I remember this. Return true if there is a 132 pattern in nums. Otherwise, return false. Do you remember? I don't remember at all, but I remember I've done this before. So basically, we're saying if I have position I smaller than j smaller than k, then I need to find nums I smaller than nums k smaller than nums j. Alright, so this j is the largest, so we want to find I, j, and then k. Right, k is in the middle, j is the largest. So this is the pattern we want to find. And we want to know if there exists a pattern like that. So yeah, so the small, the big, and then something in the middle. So you have this one, if 1, 2, 3, 4, and the next one is 3, okay, then 1, then 4, and then 2. Yeah, this one exists. What do you think? Maybe, because yesterday's monotonic array, maybe that's a hint. You want to try monotonic array? We can try monotonic array. So when you do monotonic array, what we are saying, let's just say monotonic increasing, okay? So whenever you find something small, you just pop. So basically, if we do monotonic array, right, will be 3. And then if we find something small, we'll just pop it. Now it becomes 1, 4, and then we found a 2, right? And then we'll pop it. And eventually, if there is something in there, then we say we found it, right? So basically, if you do monotonic array, your criteria for checking is when you pop something and eventually you hit, right? You're not the first one, then it'll be good. In this case, -3, 3, 2 coming in will pop this, and then this one. Yeah, maybe monotonic array can work, right? Because monotonic array in this build up, if we do the monotonic increasing, it's always this, right? This is always increasing, and then we finally find something smaller, then we start pop. Right? Pop. As long as we don't pop everything. If we pop everything, then it doesn't work. Right? Like if this one is super small, then we pop everything. That doesn't work because we want I to be smaller than j. Oh no, hold on. No. I think I got it wrong. I, j, k, we want I to be small, k to be the biggest. No, j to be the biggest. No, that's right. It's right. It's this. Sorry, I wasn't thinking. Yeah, we want this k to be in the middle. So it is, I think, monotonic array, right? Because this, you start popping as long as you have something in the front. If there's nothing in the front, then yeah, it's just it doesn't work. Like if we have, let's say 1, 2, 3, 4, and then 0, right? 1, 2, 3, 4, 0, it doesn't work because 0 is the smallest, right? Nothing in this is smaller than 0. That doesn't work. Okay, so let's try monotonic array. Yesterday I got an email from JetBrain asking me if I want to renew the IntelliJ, and then I also have data grip, and I say, yeah, I want to renew as a student, so I'm still using those for free, but very soon I'll start paying for it. All right, so that's a stack, right? New array list, and what we want to do is we definitely put the first one in it. Okay, dot append. Holy crap, n could be 1. So I should just say if nums.length is smaller than 3, and we just return false, right? You can't have a 1, 3, 2 pattern if it's like that. Otherwise, you can just add num0. No. While for int n of nums, okay, while stack is not empty, okay, and stack dot get stack dot size -1 if that is larger. Oh, what if equal? Let's pop equal as well. Larger or equal to n. In this case, stack dot. Holy crap! There's no pop. Remove stack dot size -1. All right, so remove it. I hope remove. Yeah, I think if you remove the last, it is 01. Alright, so, oh, what the hell? It's always false. Nah, because we haven't added something to it. Right? Once we done that, now we need to know if it really pops something. Right? Then we shall have a flag. So we will have a Boolean flag. We call it popped. Well, initial will be false. Okay. And no, I don't initialize it because I will initialize it here. Every time it popped, we say popped equal to true. Okay. And then gets out, we say if popped, okay, and stack is not empty, right? If popped and the stack is not empty, which means there's something, and then this is the case, we can just return true, right? Otherwise, we say stack dot add n. Then we'll just keep going, keep going, keep going. And at the end, if everything comes out, we never return true, then we shall return false. All right, let's give this a shot. I've been having some bad stretch these days. Never have I ever get them all correct in the first shot. But this one looks promising. So let's do that. Okay. Let's do a random thing. And let's do this. Okay. Let's do 2, 2, 2, 2. Just throw a bunch of at it. All right, I think we can try it. Oh, Nope. Got it wrong. Yeah, one of the more difficult questions I remember. So it's fine. Nums. Okay, and find pattern. Nums. But before I debug it, let's first check what's special about this. 3, 5, 0, 3, 4. The pattern is 3, 5, 4. And the way I'm doing it, oh, I do 3, 5, and then 0 will cancel out all of them. Then 3 and 4 and say, that's false. But, that's why it's hard. That's why every time I just got so many wrong and then accepted. I'm not even sure if I did it myself. Yeah, how do you handle this situation? Yeah, monotonic array, this will... Maybe we can consider, I don't know. Because I need this and this, right? What else can you think? So basically, when we find a value, then we want to know if the value is all decreasing, or if it's the same, then there's nothing we can do, right? If it's go this way or to go this way, then there's nothing we can do. These are not useful. I mean, yeah, I think these are not useful, because if it goes down, then it cannot be the second one, nor can it be the third one, right? Like in this one, definitely you'll want the smallest to be the first one. So if it goes down, okay, then we don't care. We pick the first valley, okay? We pick the first valley. And then if it's a valley, then we start going up, right? Yeah, because it's going to be like this. We say we'll ignore all the downtrend until we find the first valley, okay? When we find a valley, next we know it's going to go up, right? It's gonna go up, and then when it go up, I don't care because I just want the highest. So we find the valley, and I find the highest point. So that's like a pair, right? That's a pair, and then it will go down again, right? It will go down again. So if I record this and record this, and now I know it's going down. So when we go down, we don't want to find the next valley. We want to find someone in between. If it's larger than this, then we're done, right? So in this case, we have 3, then we have 5, okay? Then we drop down, okay? So when we drop down, so we say the previous pair is 3 and 5. So 0 now is a new one. Now we go up, right, to 3. Now we go up to 3. Now we go up to 4. So every time, so we drop down, and this shall be a new, right, a new one, because it's 0, 3, 4, so that's new, right? But while you go through this, you need to see if they're in between this. How do I check if they're in between this? And then what I'm thinking is, if you find this one, if nothing is in between, you find this stretch, then you can have a new one, like a 0 and 4. But how do I know if the current one is in between this? It's a good question. Nah, no idea. Think. 1, 3, 2 pattern. I don't remember how I dealt with it last time. So many solutions in the past. So a difficult problem remains difficult, huh? What was I thinking back then? I did it. I don't remember the solution at all. Yeah, how would you like systematically solve something like this, right? Maybe what, 2 pointers? Well, if you have 2 pointers, or let's say you just want to find I and j, right? I and j, and when you find an IJ pair, right? You find an IJ pair and you want something in between that's bigger. So you start from some value, okay? Then you start going right. And each time you find something that's bigger, you will ask if there's anything bigger in between. How do I know if there's anything bigger in between? Oh, we can like keep a local max. But yeah, that's O(n) squared. Like, it's not gonna work. Maybe 2 monotonic arrays? I mean, we can do an increasing. I mean, this one do increasing will give us 0, 3, 4. Right? So we know there's this, that's the smallest. Okay, 0, 3, 4 is increasing. And then, if we do a decreasing, monotonic decreasing, that's actually going to give you 5, 4. Oh, what the hell is that? It's going to give you 5 and 4, right? Monotonic decreasing. That doesn't make any sense either. But basically, you do that, they give you the maximum or the minimum, right? So you know, in an array, you have the minimum, and then the next one and the next one, right? 0, 3, 4, and there might be something higher in between, right? It's possible, or not, right? Or not. But how does this help? So it's monotonic increasing. So we want to know if there is anything in between. Then the answer is no, there's nothing in between, right? There's nothing in between. That's bigger than all of them. And if we do decreasing, right? We do decreasing. Or we can say monotonic increasing from right to left. So we have 4 and 3. Actually, 3 will come here. 0 actually doesn't come here. So that's actually going down, right? 4, 3, 0. So we have a 0. And then 5. And then 3. So actually, it will be 3, 0. That's not helping, right? That's not helping. Five, 3. Yeah, now you want to know if there's anything before that's smaller, because it's monotonic decreasing. So everything comes in, there'll be something small. Okay, something small in the past. Okay, I have something small, and now you're big, so you'll pop it. Something small and big, pop it. So you'll keep the smallest. Okay. So if you do monotonic decreasing, you can keep the smallest on the left hand side. Okay. And as you go, you go bigger, 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 right? And then you basically will accumulate to the biggest value. That one will stay. Okay. Then you start to hit value on the right hand side. Doesn't matter, right? So let's just say, yeah, let's say you have something, you know, you just go here and then you go big, big, big. We don't care if we keep just the minimum value here and you hit a maximum, the current, right, just go up. But if you go down, you record everything, right? If you go down, you record everything, but that doesn't matter either. So, but you keep a track of the minimum value so far, okay? And then you'll go up, right? You hit some value, then you start going down again. So on the down, right? And if you hit something even bigger, and that doesn't matter because as you go down or as you pop, right? Just you reach the next peak, right? Not next peak, the next one that's bigger, then you need to pop these, right? And these things, while you are getting popped, they are smaller than this. Then what we want to know is if there's any value in here. So if we keep the minimum value as you go through, okay? If you keep the minimum value on the left, you just always keep track of the minimum value, okay? And you do a monotonic decreasing array. So we do a mono decreasing array, okay? We do a monotonic decreasing array and we keep track, okay? I'll say keep track of the min on the left, right? Then each time we pop, we compare to the minimum on the left, right? On the left. And we will update. Well, because it's going this way, right? So if we pop, if this is already bigger than the mean, then we already found it. If it's smaller, then we keep track of it, right? Well, yeah, because it's decreasing, so this is definitely the current smallest. So we keep this, right? We remember this, and then every single time we will pop, because this one is at a certain point, right? This is at a certain point. If this one's really big, right, then we'll pop everything, right? We'll pop, because it will be like this, and if I have a really big one, and then we'll pop everybody, and everybody as I'm popping, I'll compare to the previous minimum, and to see if we can find it. If nothing, right? If there's nothing, then if there is nothing, like all of them are or there's no previous, right? Because I want to know if someone is bigger than the previous. So the previous we can get, you know, initialize the maximum, right? So if nobody is, right, then after we pop, then yeah, because nobody is bigger than that, okay? Nobody is bigger than, everybody is smaller. That's not really possible, right? Because you pop some stuff, so these definitely will be small. Something here will be small. So we have the minimum, right? We have the minimum until this, okay? So this is the minimum on the left, the smallest. It's definitely smaller than that. And then you just do, okay? And then you pop. So one of them is bigger, then we're done. But if they're not bigger, if they're even smaller, which is possible, right? What if they're even smaller, right? If they are like here, they're even smaller, and then you get some value in, and then you pop this. And I say, oopsie doozy, no good. You pop this, oopsie doozy, that's no good. And then this is kind of jagged in the middle. Then what? Right? Then what? Do you put this, because these are the small values, right? These might be useful. So what if I add them together, like the previous, the minimum, then we pop this. Oh, and then they say this is smaller than this. And then we pop this, and we put in here. That is not. They're not sorted though. They're not sorted. No, they're not sorted. Well, if I can keep them sorted, right? And every time you pop, because every time you pop, you know there's something bigger. So you just need to know, hold on. Every time you pop, right? Every time you pop, you know something is bigger ahead of you. You know that. So all you need to know is in the previous, is there anything smaller? Is there anything smaller in the previous? That's what you want to know, right? That's what you want to know. So what we need to know is at this peak, right? At each peak, what is the smallest value to the left of this peak? If I know that, right? Then when I pop, before I reach this peak, then I will compare to this to see if it's good or bad, okay? But now I have something in there that are causing these to pop. So when we pop, we also keep track of the smallest, right? Keep track of the smallest. And then if we pop everything, then we'll have, this is the current peak. Then we'll record what's the smallest up into this, right? Otherwise, we will, if this one gets kind of stuck here, then I need to know what is smallest up until this point, which means it has to be everything that's popped compared to this will be this value. So I can have, let's say I have an array, okay? I have an array, and their position will be the minimum up until this value. This position, the minimum up until this value, okay? So now as I go, a new one comes in, and I start popping again. The new value will start popping again. And every time I pop, okay, every time I pop, I need to look to my left to see what is the minimum value up until that point. Now it's this sounds promising, okay? This sounds promising. So basically, we'll have an array, right? We call it the pre-min array. Then we say pre-min I is the minimum value in nums all the way to I. Okay, inclusive. Dude, I can create this. I can create this. I can create this. Come on, I can create this. That's not hard. So in this case, let's just try it. Let's try it. I can create this, right? I can create this. So this one is 5 values, right? So 1, 2, 3, 4. So the prefix min will be 3, 3, 0, 0, 0. That's the prefix min, right? Yeah, up until this point, what's the min? That's prefix min. And then I'll do a monotonic decreasing array. Okay, decreasing array. And each time a number popped, okay, we compare it to the pre-min, right? Yeah, every time it popped, a value popped, because monotonic decreasing. So if we have something bigger, we'll pop, right? Those values will get popped. So every time we pop, unless you're the last one, and there's nothing in front of you, or you are the smallest. Hold on. We're almost there. We're almost there. So we have a prefix minimum, right? And then every time you pop, because it's monotonic decreasing, okay? So every time you pop, it's very likely you have somebody. So yeah, you check every time we compare it to the pre-min of the value to its left, right? To its left, the position of the left. So if this value gets popped, right, I check this, the minimum up until this, right? We check the minimum up until this position. And if this one is larger than that, then we're done. So we have a 1, 2, 3, 1, 3, 2. But if the previous minimum here is not smaller than this, then we just, we'll pop this. Then we go here. Then we'll try this. And we'll try this until we are heading at the beginning. Now, if we're heading at the beginning, we don't have anything to the left. So yeah, so this is nothing. So with that in mind, I'd like to try to run this. So I have 3, okay? Monotonic decreasing array, which means if we go 5, we will pop this, right? We go 5, we'll pop this. So every time we pop, we check the previous. There's no previous, so bad. Now we have 5. Now we have 0, no pop. Now we have 3, then we pop 0. Then when we pop 0, we check on 5, right? It's previous min. Previous min is 3, which is larger than, so it's no good, so it gets popped. But 5 cannot get popped because 3 is smaller than 5. So now we have 3, okay? Now if 4 comes in, we pop 3. So we look at the value in front of 3, which is 5. Its smallest is 3. So this one also doesn't work, okay? So now I hit everything, and then, I need to add another one. Another huge, we add another max comes in. Now I pop 4. When I pop 4, I check 5, which gives me 3, and then boom, 3 is smaller than 4. Then we're done. All right? Let's try another one. Yeah, this one's promising. Let's try this one. Right? Easy peasy. 4. So we have 3, 1, 1, 1. Right? That's the pre-min. So 3 comes in, 1 comes in, 4 comes in. 4 comes in when you pop 1. Okay? 1 and 1 doesn't work. And then 4 so pop 3 doesn't work. Okay? Now 2 comes in. Nothing. Okay? But at the end we'll get a max come in. So 2 will get popped. 2 get popped, look at 4. At 4 position previous is 1. 1 smaller than 2. We got it. That's nice. Alright, let's do one more. One more shot. Oh, I think this is a solution. Okay, so it'll be minus, or it'll be just all -1. That's the pre-min, right? Now monotonic decreasing, -1, 3, so in the pop -1, nothing in front of it. That's it, no good. 2 and 0. Okay, now we'll do a max. Max come in, pop 0. Look at the previous one, -1. It's good, right? It's good already because it's like -1, 2, 0, right? -1, 2, 0. So yes, I think we got this. I think we got this. It is a monotonic array, but it's oh, we also need a pre-min. Okay, so we need to have an int pre-min, okay, equals new int nums.length, okay, and then we do, what do we do? For pre-min 0 will equal to nums 0, right? And then for int I equal to 1, I smaller than nums dot length I plus plus. We do, what do we do? Num pre-min I shall equal to mass dot minimum pre-min I minus 1 and nums I. Okay, so this will get a pre-min, and then stack. We shall make sure that we know what type of stack this is. This is a monotonic decreasing stack. Okay. Now what we're gonna do is we will. Oh shoot! It's more than that. I need to push 2 things in it. Sorry, I need to push 2 things in it. So it will be int. Okay. And I cannot do this. I need to say I equal to 0, I smaller than nums dot length, I plus plus, right? Then what? Then we say while stack is not empty, and stack dot get the last one. Okay, the last one is 2 values. So let's call it we say stack I equal to index and value. Okay, so 1, right? If this value is smaller, right? Because we go to decreasing. So if it's smaller equal to nums I, that's when we'll pop, right? If it's bigger than me, then we don't pop. If it's smaller than me, right? If it's smaller than the current one, then we'll pop. Okay. We'll pop. We'll pop. But I need to pop the value. Does this return anything? Remove the element. Return the element that was removed. Yes, it does. So we can say int popped equal to this, right? Or remove the popped. And then we will say if, right? If, oh, I see what you're trying to do. Can I add another value to this? Nums? I don't think so, because it's not a... Oh, we'll deal with this. Don't worry. We'll deal with it at the end. So now we got things popped, right? So we popped, then we need to check if... if stack dot is empty, right? If stack not empty, and popped 1, the value is larger than Popped value is larger than, oh, what if the previous min? Yeah, so we have to check two things. If popped value is larger than pre-min, oh, holy crap, there's so many things. Okay, let's do it this way. Let's do it this way. So when I say int pre is stack dot get stack dot size minus 1, right? Because I already removed, that's fine. So I have the popped, and then we have the pre, right? And, oh, actually no. Actually no, it has to be if not stack dot empty. If it's not empty, right, then we can get the previous one. So we have popped, we have the previous one. Now we say if popped one is larger than pre-min previous one 0, right? And pre-min 1, which is the value, is larger than pre-min pre-0. Okay, so this is your k, right? K need to be larger than I. This is the I. And j, this is the j, need to also larger than the previous min, right? And then we know the popped is smaller than this. So if that is true, then we'll return true. Done, right? If not, that's fine. Then we just, forget about it, keep going, and at the end we will stack dot add new int, okay, index nums I. Right, so we'll do that. Right, we'll do that until the end, but then it's not over, because we need to have one more, right? So that is when we shall say if, right? If stack dot is empty. If stack's not empty, then we'll do one more round, right? One more round. Basically, we'll do. Yeah, it does look like will be better if we can put the numbers into. Yeah, you know what? Maybe we should do a list of integer extended nums equals to list dot of nums. Okay, and need to play a trick. It doesn't work. I never remember how to do this. Arrays as a list. Oh, you have to do. Oh, Jesus. I just want to put the. When you do that collection stuff, right? Integer array dot stream. dot boxed dot collect. Jesus, give me a break, man. Give me a break. I'm not doing that. I will do it here. So we have this, and we have a list of integer extended nums. Okay, go to new array list, and then we say extended nums dot add nums 0, which is fine, and then extended nums dot add nums I, which is fine, and at the end extended nums dot add math dot not math, integer dot max value. I think that should be fine. 10 to the 9th, this is bigger. Okay, now we can say extended nums. So instead of doing nums, right, we'll do extended nums. And it's not length, this is size. And this is not this, is empty dot get, right? Dot get I. And this is extended nums dot get I. Okay, let's just make sure that the indices all work. Yeah, and now we have extend, so everything will work until the last one, and then we don't have to check at the end, so we can just do that. All right, so let's see. This shall return false. Expect is true. Dude, what the hell? Come on. That's okay. Let's see what goes wrong here. All right, this is right. Then we go, let's do F8. Extended nums. Yes. Okay. Well, the first one is empty, so we add 0 and 3. Okay, so we need a stack as well, 0 and 3. Okay, next one is 5, so we need a pop. Right, so we get a popped is 0, 3, and stack is empty, there's nothing in between, in before, so nothing happens. So we add 5. Now stack size is 0. That's weird. Wait, hold a second. The 5 is not added to it. What? Hold on. I'll add 3, right? Next one. Stack.get size at the end is 3. Nums.get I is 1, is 5. It's smaller, yes, so we pop. Right, is false. Okay. So extended num stack now is empty. Why am I not doing this one? Yeah, why am I not doing this one? Oh, hold on, it will. It's just at this point, it'll be empty. Now we add, okay, sorry, I wasn't thinking. Okay, yeah, we add this. So we have 5. Next is 0. This will be false. So we don't do anything, get out. Okay, so we got 0 in. Next one, we got 3. 3 will pop. Right, so we'll pop the 0. And stack's not empty, so I can check the pre. Pre is 5, right? and then popped 1 is 0. Is it larger than the pre-min? No, it's not. That's why it's a false. So we don't return anything. Go back up. 3 compared to 5, failed. So get out, we add 3. Cool. Everything's fine. Now we have 5, 3. Last one, 4 comes in. We'll pop 3. And then we'll compare to 5. Right, which is false. Good. Get out. Get out, and add 4. Perfect. Now we have 5 and 4. Now, last one, right? Last one. The current value is maximum. Okay, so we'll pop. Okay, stack. So we have 5 in there. So 4 is popped, right? So so popped 1 is 4. Yeah. Pre-min is 3. So we'll come here. All right. Pre-min. Oh, that's not pre-min. I see. That is pre. That should work. Sorry, pre. There we go. All right. Let's try. I put this one in. A bunch of other test cases. There we go. All right. Come on. Show me. Show me. Yes. 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 I think I did better than before. That's all that matters, you know. I've been just having such a bad stretch, and this is a good boost, okay? A good boost. I mean, that's it's good. But I wonder if we can make it a bit faster by not using this. Right? This is an extra copy. So what we can do, what if I write this as a function? Yeah, I think you should write this as a function. Let's see if we can write this as a function. We can say, what does the function do? Just, you know, we call it private, okay, boolean manage mono array, mono stack, okay. So what we need to have is a list integer of a stack, right? What we need to have is the current, so an integer of the current, and we need to have a int pre-min equals, now I don't know what this is, in the pre-min, so I don't have to do that. And yes, okay, then we'll put the entire thing, this entire thing, okay, I'll put this one inside here. Okay. This is not. This is going to be current. Why are you complaining? Oh, my bad. Int this. Okay. And then, yeah, like we'll remove, we'll do whatever, right? We'll do whatever, and then we'll return true. If not, we'll return false. Okay. Then we'll say this I could just say premin, right? And then we don't need this extended. We don't need these. We do not need this. We definitely do not need this. And will be stack. And all of this will be regular nums. Okay. Regular nums. Oh, then that's not size. And this is gonna be I. This is gonna be length. Okay. Now we're just gonna call manage this, so we'll call stack. Current is nums I. Right, now we say if this is true, then we return true. Right, otherwise we do this. Once we're done, we say if stack is not empty, is empty, is not empty. But you know what? We can actually, we can return manage this stack and integer dot max, integer dot max value, right? So if we have stack, then we put a current, it will do whatever. If the stack is empty, right, we don't have anything in the stack, then this won't pass, then we'll return false. So with that, I definitely save time. I don't have to create another extended array. Okay, so this, and make sure everything's fine. Everything's still fine. I think this will be faster. I think it will be faster. Yes, yes, yes. That's the one. This is the one. Oh, I'm happy. I am so happy. We got this. We got this. 4, 5, 6. Okay. Oh, struggled a lot on this problem in the past. So I am very pleased that we got only a slight hiccup, right, before finding the right solution. I have to admit that although I didn't remember the previous solution, I vaguely knew the solution has something to do with monotonic array. This helps reduce the search space of all potential solutions. The insight, the most important insight, is that monotonic increasing array does not work. And then when I switched, to monotonic decreasing array, I realized that when numbers get popped in a monotonic decreasing array, it is guaranteed, as long as the stack is not empty, it is guaranteed that we have some value to the left of the popped one that is bigger than the popped one. Thus, we only need to ensure that some value to the left of the bigger value currently in the stack is smaller than the popped. Then we will have found the 132 pattern. To quickly find the smallest value, right? To quickly find the smallest value to the left of any number in nums, we need a prefix, right? A prefix minimum array. I'm guessing maybe we don't even need that, but I think I'll just keep it. All right. Then everything is fine, and we can say on on this. Cool. All right, let's just handle the last couple pieces. I will read. Some stuff. Okay, I'll put this one up. Right, this is for today. I'll just check the previous solution. Yeah, that's a prefix min. Stack. Potential third value. Oh, I go from right to left. Hold on. What is a stack? Potential third value. And then if previous min is larger than the current bag, then yeah, it's useless. So we pop it. Okay. Now we find something that's the previous min. So at certain positions, previous. So we have a monotonic. I think. I don't even know what type of stack is this. This is searching for the second value, right? The third value, this is the big one. So we want previous min need to be larger or equal to previous min. No. Previous min, if it's larger than the stack. Stack is going from right to left, right? If previous min is larger than this, it's not going to work. So previous min needs to be smaller than this, right? And then if there is still a stack, and then oh yeah, this one works as well. This one works as well. So this one basically we go. Let me see if I can draw this. We have a pre-min still, right? We have a pre-min still, whatever it is. And then we go from this direction. So every time we pop out, we get this one, and then we go a monotonic increasing. So we say a monotonic increasing array. So every time we get this, we check the previous min. So this is the third value. So we check the previous min here. So that's the first value, right? And if the first value is larger than this third value, it's useless. Pop it. We don't need it. Okay. And then because this is monotonic increasing, right? So every time a new value comes in, right, we check the previous minimum, and if it's larger than, we pop it. Now we check this. Yeah, are you larger than? Pop it. Oh, now we find some position. Okay, some position previous min is smaller than this. Okay, so we have a potential first, we have a potential third, Now we need to know is, no, this is, we have the potential first value is the min, right? And we have the potential third value. Let's say second value. Hold on. I don't think this is right. This is the potential third value. The things we put. No. The things we put in the stack is the second value. So yeah, it's going to be the second value. Right? So we are at I, num's I, right? Num's I. I find its smallest, right? And then we try to compare it to the previous one that we have seen. Those all potential third values, right? These are all potential third values. So if at this position it's minimum, right? Which is say at this one, I find its minimum, I know it's minimum, and then we compare it to everybody on here, and then we keep this is the increasing. Yes, every time is bigger, we'll put it in. So these are all the big values. Here's all the big values. So we compare. So this has to be smaller than that, okay? So if we find this one is smaller than this, smaller than something, right? And this is increasing. So if this is smaller than the first one, you get smaller than. Then you compare your value. Your value has to be larger than that. If it's larger than that, then we find 1, 3, 2. If this is smaller than this, what if it is smaller than this? There's still a chance, don't you think? Because it's increasing, right? So if this is smaller than that, but you are not bigger than this, there might be another one. Huh. So this is larger than this will pop. Larger than this will pop. So we'll make sure everything in here, right? So what we make sure is everything in here is smaller than, no, bigger than the min. Okay, everything here is bigger than the min. Then we just need to know if this is bigger than that. If it's smaller than this, then we add it. Oh, I think this is a monotonic increasing array, right? This is a monotonic increasing array. No. Hold on. It's not increasing. It's a monotonic decreasing array on here. It's a monotonic decreasing array because so this is always going down. And if this is bigger than, so yes, it's a decreasing array. And then we have the minimum value. And then we say all these are larger than the minimum. Okay? All these are larger than the minimum. So now in here, if I am bigger than this, then we're good. Right? Then we're good. If I'm smaller than that, just keep adding. So this is always going down. It's always going down. So if you find the first one, as long as it's bigger than this, yeah, we have the highest chance of success. Let's implement this as well. I like this. I'm pretty sure I didn't come up with this myself. So that's the improvement. Okay, so there will be another solution. We can say this is a solution. So this is the solution I submitted last year. I'm pretty sure I didn't come up with this myself, and because it was quite brilliant. We use a pre-min array as well. Then we go from right to left on nums and produce a monotonic decreasing array. The trick here is that we must ensure that every value, every number in the monotonic decreasing array is bigger than the premin of the current value. Then everything in the monotonic decreasing array is a potential nums j is a potential nums j. The premin value is a potential nums I, a nums k, right? All we need to do is to check whether the current value can be nums j. Now we know the current value must be bigger than nums I, right? Must be bigger than its premin, right? Must be bigger than its premin. So we need to check whether it is also bigger than the smallest of the monotonic decreasing array. It just so happens that the smallest in a monotonic decreasing array is the value on its tail. Then voila, we have a check for the 132 pattern. Done. This is ON. Okay, so int, right? We have this. This is good. We have this monotonic decreasing as well, but we can just do int integer. Now we need to go from right to left. Right to left. So we say nums.length -1. I need to be larger or equal to 0. I need to minus. And let's say we don't need to manage. We just do it right here. While the stack is not empty and premin I is larger or equal to stack.get stack.size -1, right? If it's larger than this, then stack.remove stack.size -1. So this is to ensure everything in the stack is bigger than premin. Okay, so once we get that, then we just say premin I is the potential first value. Stack -1 is the potential third value. So we need to check if nums I, right, is larger than premin I, and nums I is larger than stack.get stack.size -1. And of course, we're also going to say if stack is not empty, right? Dot is empty, and when this is the case, then we return true. Otherwise, stack.add nums I. And if nothing happens, then at the end we'll return false. Okie dokie. Put in here, run this. Nice. Ah, similar. Good. I actually like my solution better. This one is a little bit tougher to wrap your head around. I think my solution is more straightforward, right? This one's I think this one's more straightforward. This one's more straightforward. You just, you know, do a monoculture decreasing, and every time you pop, right? Every time you pop, you try to check. You pop, you try to check. But anyway, that's it. Good. I will see you guys tomorrow. Adios.